Make sure I'm unmuted here. Hello, hello, hello. As some of you, I am sure, are well aware, a couple weeks ago now, this is probably I don't really know when it happened, but this would have, 4 days ago is when this premiered. So I'm assuming the discussion probably happened a week or so ago. But there was a discussion between Phil Halper, Skydive Phil is what his channel used to be called here on YouTube. He's been doing YouTube for quite some time. I think I actually first found his channel in like 2017 or 2018 or something like that. Started with sort of interviewing a lot of physicists as it relates to Big Bang cosmology and, extending the history of the universe beyond the Big Bang and all that stuff. I'm pretty sure the main series on his channel is called Beyond the Big Bang, but don't quote me on that. I think that's what it's called. He had a discussion with Stephen Meyer. This was on Justin Brierley's no, I'm thinking of something else. Uncommon Ground. Okay, that is what it's called. All right, I was thinking it was called something else. This was an almost 3-hour long discussion. I will not be reviewing the whole thing here today in this stream. They talk primarily about the more Kalam cosmological argument, as well as the fine-tuning or the teleological argument. So this review is going to be in 2 parts. This first part we're going to be reviewing their discussion with respect to the Kalam cosmological argument, and then probably sometime next week I will do another stream talking about fine-tuning, going over their discussion on fine-tuning. But this is Stephen Meyer and Phil Halper with Justin Brierley having a discussion on cosmology and the Big Bang and fine-tuning and God. This was actually a really packed discussion. There was a lot of information in this. It doesn't really get like super technical, but some stuff might go over the average person's head. I'm going to do my best to explain things. I've skipped ahead a little over 25 minutes here. This is just like introductions. They kind of introduce themselves, talk about their books. I don't really care about all that. So we're going to jump right in. They start here with, is there a conflict between science and religion? And we'll go for about, I think it's about a little over an hour of the discussion from here before we stop. So I guess without further ado, let's get started.
Let's start actually just with the broad theme of science and faith. I mean, Phil, do you feel like there is a fundamental conflict between believing in God and
hold on,
doing good science?
Give me a second here.
I think doing good science,
that fixes that.
Definitely not. Okay. Like, no question. No, you can be a religious believer and you can do good science. There's no question about that.
Where does the conflict lie, if there is one?
So, and let me give you another common ground between Stephen and I. There's this thesis that historians of science use called the Draper-White thesis, and it says that the relationship between science and religion is one of perpetual conflict, and I think that's false. I think that's obviously false. So I don't sign up to the Draper-White theory, and I don't think there's any conflict between being a religious scientist. That's fine, but I do think there are what I would call is a probabilistic conflict. So let me try and unpack what that means, and it goes back to something that basically, if you go back to, let's say, Tycho Brahe, who was, for those that don't know who he was a very famous astronomer, and he was like the greatest astronomer of his age just before the telescope. And he examined the Copernican model. Oh, I say Copernican model. Actually, Copernicus didn't come up with a heliocentric model. It was Aristarchus of Samos about 2,000 years earlier. But anyway, he didn't necessarily know about that. But so the Copernican model came out, and Tycho Brahe says, he gave arguments against it from physics, but he also said, but it contradicts Holy Scripture, which must be paramount. And I think science today says not only is Holy Scripture not paramount, but it's not to be considered at all. And so whereas, of course, in the religious tradition, or in the Christian religion tradition, which is, the one of relevance here, because, Stephen's a Christian, 2 Timothy says all Scripture is God-breathed. And then you have this tension, right? What happens when Holy Scripture seems to contradict the consensus in science? And of course, there are many things that Scripture, at least on the face of it, says that do conflict with science. So the world is not 6,000 years.
Yeah, the point that Phil is making here is that First off, the claim, is there a conflict between science and religion, isn't really like super clear cut. There's a little bit of nuance there. What do we mean by conflict? What kinds of conflict are we talking about? But I do agree with him generally that there is sort of a conflict between science and religion, in that religious traditions, at least prima facie, oftentimes run counter to what the consensus of science tells us, such as the age of the Earth, how the Earth or the world, the universe was created, various ways that life was classified 2,000 years ago, stuff relating to medicine. It gets a lot of stuff wrong. And in order to maintain both your belief in the science and your belief in the religion, you would either have to reject those parts of your religious doctrine, or you'd have to reject those parts of science. But you couldn't hold both of them at the same time. And so in that sense, there is just fundamentally a conflict between science and religion. Now, there can be a discussion as to I guess, sort of the seriousness of that conflict. I don't think it's very serious. Most people would probably reject a lot of the religious doctrine there, such as the Earth being 6,000 years old, or something along those lines, the Earth being created in 6 days, some stuff like that. I don't think that it's wrong to reject those. I think one should reject those, and I think one can still be religious. I think one can still be a Christian and reject those things. But the point stands is that there still is a conflict there between what the religion is teaching and what science tells us.
Years old. There wasn't sort of primordial water. There's not a solid dome of the sky. It wasn't created in 6 days. And on we can go with many, many examples. So now, with that in mind, there are sort of 3 positions I think you could broadly take, right? One is to embrace the science and reject the religion. 2 is to embrace the religion and reject the science. Or 3, find some way to reconcile them. But notice that 2 out of those 3 strategies is going to lead you into a conflict. And we have some data. That's all hypothetical, of course. We actually have data on what people really think. So there was a survey in Time magazine of Americans, and they were asked, what would you do if a scientific fact contradicted an element of your faith? And 64% of them said they would reject the science. There's surveys of how many people think the world is less than 10,000 years old. And the answers do often depend on how you phrase the question. But it's somewhere between sort of 20 and 40%. Surveys of people on climate change, we find something like 90% of atheists accept the science. About 45% of Christians do, about 32% of evangelicals do. So what you find is
that American evangelicals are really fucking dumb.
That's why I think it's a probabilistic conflict. It's not that religion, or Christian religion in particular, forces you to oppose science, but what it does do is increase the probability that you will.
That's Halper way of putting it. Yeah, in real life situations, if you are a Christian, you're more likely on average to be skeptical of certain.
Yeah, it's just like smoking, right?
By the way, I have watched this whole discussion before doing this. I know I don't normally do that, but I wanted to listen to this, and I decided after hearing it that, you know what, I'm going to do a couple of reviews on this. I actually think Justin Brierley, not that I don't really have any issues with him as a person or anything. I think he does a pretty good job of moderating this discussion. I think, obviously, Justin himself is a Christian. I think there's just a very slight favoritism towards Stephen. I think Stephen is given just a little bit more time to speak, but I do think that him and Phil, for the most part, had a relatively fair amount of time to speak. This was actually, I think, a really, really good discussion on particularly the Kalam cosmological argument and the fine-tuning argument and the defenses that are given for these, as well as what the objections to these arguments are. I think this, as I think you guys will see, this was a really, really good discussion. Something else that I want to say, that I know there's going to be a lot of detractors to what I'm about to say, but I think it's true. I think Stephen Meyer is a lot more formidable than people give him credit for. I think he's a lot more knowledgeable than people give him credit for, and I think he's pretty rhetorically skilled. Compared to your run-of-the-mill evangelical apologists, you think somebody like Frank Turek. I mean, even amongst your typical apologist at specifically the Discovery Institute. I do think that Stephen Meyer is a cut above them. I think that he does a better job in his defense of his faith than even other people at the Discovery Institute do, let alone people like a Frank Turek or something like that. And like I said, I know there's going to be people that disagree. Oh, it's Stephen Meyer. He's just an idiot. And I'm not saying he doesn't get things wrong, as we're going to find out. But I do think that he is more formidable as an opponent than a lot of people give him credit for. And I think this discussion reveals that.
Right. If you smoke, you're more likely to get cancer. Does it guarantee you get cancer? No, it doesn't. Could you get cancer without smoking? Yes, you can. Right. So similarly, you can oppose science and be an atheist.
Well, it'd be interesting your perspective on this, whether you broadly agree or not with Phil's take on the probabilistic way in which
it's a very nuanced way of explaining the view he has. I found that illuminating. I've written a lot on this, and not just the origins questions, but just on the models that people have developed for capturing the relationship between science and religious belief, biblical faith, if you will, and specifically. One of the things, we're starting a new center in Cambridge called the Hewell Center for Science and Natural Theology. And one of the things that's very clear in the history of science is the very important role that Judeo-Christian, that is biblical assumptions, played in the foundation of modern science, particularly in the period that historians call the scientific revolution, and that natural theology itself played a very important role in that. I'm quite a fan of the work of John Ray, who's often regarded as the father of modern botany. Turns out that Ray was very close with Isaac Barrow, who was Newton's tutor, and there's this tradition of natural theological thought in Cambridge that was crucial to the rise of the scientific revolution. One of my Cambridge supervisors, historian of physics, told me when I was doing work on the debate about universal gravitation in the 17th century, he said, if you miss Newton's theism, you've missed everything. The Principia was a theological project. So I find I like that Phil has.
I mean, if that's true, there's not a lot of theology in the Principia. Within the Principia, it's primarily him outlaying the methods of basic calculus that he uses in his derivation of his laws, and then his derivation of his three laws and an explication of what they are, his understanding of gravitation, how his laws recover Kepler's laws. That's all in there. I mean, obviously, this is the mid-late 1600s. Isaac Newton, rather, it mentions God, creator, a couple of times in it. But I'd say it's far from a theological work. Now, did Newton's faith play a role in how, helping to motivate him to look at things a certain way? Of course. I think that's very much true for a lot of scientists, primarily from like the 1500s into the 1800s. But I don't think that, and Phil pretty much gives all the responses I would give here as well. I don't think any of this means that Christianity is unique amongst institutions in its contributions of science over and above all of the other institutions and all of the other sort of cultural practices that have, without a doubt, influenced science and helped to develop science along the way throughout human history.
Rejected the Draper and White thesis that science and religion have been always at odds and are intrinsically so. Then that's the sort of conflict model. The alternative, I like to think of this in terms of propositions that you have. There are propositions that come out of the scientific endeavor. There are propositions that come out of a biblical text or out of a theological tradition. And those propositions can either disagree, in which case you have conflict. They can often be talking, or they can agree, in which case you have some kind of harmony or concord or agreement. Or they may be propositions that are addressing different topics altogether and can neither agree or disagree. And so there are four basic models that people talk about when they talk about the relationship between science and faith. They'll talk about the conflict model, the compartmentalism model, a variant of that called the complementarity model, where it's not that science and religion are talking about two completely different things, but they're talking about the same thing in different incommensurable language, which also leads to the proposition that science is inherently neutral with respect to metaphysical or religious claims. And then there's a model that I've kind of developed, which I call qualified agreement, and that it acknowledges that, yes, there have been times of conflict.
Just as a point of clarification, most metaphysicians of science would not say that science is neutral on at least some metaphysical claims, that science makes metaphysical claims and that science can and does answer certain metaphysical questions as well.
It also acknowledges that oftentimes science and religion are talking about two different things. There's the famous Galileo aphorism that says that the Bible tells you how to go to heaven, not how the heavens go. But I also point out that there are many questions that science addresses that are not religiously neutral. Questions about, for example, the origin of the universe and the origin of life, and historical questions about, for example, whether there were people like Pontius Pilate and Herod Antipas and Josephus, Caiaphas and others around the time of the trial of Jesus in the New Testament. So the Bible makes factual claims about time, space, and reality. And when it does, there are sometimes points of tension, but what I have seen is a progressive increase. This is a kind of probabilistic argument, but over time, there's a progressive increasing agreement between the two. And so that's why I call it qualified agreement, that on balance, you have an agreement, but there are some points of tension where either we're getting the science wrong, or we're getting the biblical interpretation wrong, or we just don't know enough yet. So that's kind of the way I look at it. And I'm
going to say something here that you all have heard me say quite a few times because it's very much true, and it's worth repeating. Empirical facts, simpliciter, do not bear on the existence or the non-existence of God.
I find science to be, I've done physics, I've done geology, I've done biology. I love science, and I find that it can, the broad, both the approach of the scientific inquiry, the methodology of science, and the deliverances of science fit nicely with the biblical faith that I have.
Really helpful. Thank you, Steve. I mean, just starting to draw this together, Phil, from your perspective, Steve, one of the points he makes is that the very fact that the scientific pioneers were broadly speaking Christian and did things out of their Christian convictions. I don't know whether you agree with that broadly, but obviously Steve says there is this model that he believes is quite fruitful, which is this qualified agreement. Obviously quite different to Stephen Jay Gould's non-overlapping magisterium.
It's precisely the opposite.
The opposite. Yeah, exactly. Yeah. What's your feel? Is that a fruitful approach? Do you agree that science does stand on the shoulders of a number of Christian pioneers?
Well, I think, but they stand on non-Christian pioneers, right? So that's the point. Yes, of course, Newton was a Christian. I mean, unless you think his doubting of the Trinity makes him not a Christian, but I always say, yes, he was a Christian, right? So, but of course, there were lots of people that we owe science to that were not Christians. The Greeks, of course, made huge contributions to science. So, for example, the pre-Socratics, we have Anaximander. Anaximander came up with this idea that the Earth is floating in space. No one had this idea before him, as far as I know. Everyone thought the Earth sits on water. And Karl Popper, who was, very, very famous philosopher scientist, I'm sure most people will have heard of, he said this is one of the most portentous, most incredible ideas ever put forward, because it established this idea that actually we explain the world through physical principles. I mean, he said everything moves by necessity, which is some people would interpret as laws. Then, of course, you have the Pythagoreans who said science is described by mathematics. We need mathematics to describe the world. An incredible step. Then we had, people like Eratosthenes who measured the circumference of the world. They did an experiment. They used mathematics and they came to conclusions about the world. And they got the answer right within about 10%, back in ancient Greece. This is all before Christianity. Then we have the Indians. The Indians came up with the idea of atoms. They gave us the mathematical tools that we need to do modern science. Then we have the Arabs. The Arabs had huge contributions. So I think...
And then Chinese sort of...
And this is the point that I would make, is that clearly there is a sense in which Christianity as an institution had an influence on science, but it's not the only institution that's had an influence on science. And the influence that it had wasn't because science is Christian or only Christian values or Judeo-Christian values and mores could develop something like science, as much as it is that Christianity was the reigning cultural institution during these developments. So, of course, those developments will happen under the Christian lens, because Christianity is the reigning cultural institution of the time. You go to where Islam was the reigning cultural institution, and scientific discoveries were made within that or under that lens. The same if you go to India with the Hindus, or you go back thousands of years with the Greeks. So there's been a number of overarching cultural institutions through the lens of which we've made developments in science and mathematics and medicine. Christianity is not unique here and doesn't have any sort of monopoly on the development of science, modern or otherwise.
Sort of instrumentation and so
Yeah,
on.
the compass.
Well, I mean,
you know-
look, do you mind if I pass that back to Steve? Just
Yeah,
'cause,
sure.
You know, that's a helpful riposte. Pre-Christian civilization and thinkers were starting to develop these ideas, even if they were then taken further by Christian civilization.
Yeah, sure. I have very little bad to say about the Greeks, but I, in grad school, read a really interesting article, history of science article about the juridical, about the origin of the concept of natural law, and the author argued that it was a juridical concept of theological origins, and he specifically traced this back and showed that in Greco-Roman writings you have the concept of law, of the natural law, but it was the idea of the ability to access the moral law through reason, but that the idea of laws applying to nature was something that came out of the Hebrew Bible, and he cited particular passages that were of key.
I'm not sure how true that is.
Importance to a number of the founders of the period of science during the period of the scientific revolution, and so there were distinctively Judeo-Christian contributions to the rise of modern science, and one that a number of historians of science have focused on, not just the idea of lawfulness, but two others. One, the idea of intelligibility, the idea that nature.
I have to be honest. I hear this. Well, all these apologists talk about, well, the universe is so intelligible. Why is it? I think that this is just a non-issue. I don't think this means anything. What do we mean when we say the universe is intelligible? If all you're referring to is the fact that humans can understand and like quantify and qualify formally or otherwise the way the world works, that's not like a property of the world that we can do that. We can do that because we are a part of the world. If the world were not regular and were highly chaotic, we would be able to understand that too. We would just understand the world as being irregular and chaotic rather than regular and ordered. So, and there's a sense in which the world is, or at least can be, irregular and chaotic. The fact that we understand the world is because we're a part of it, not because understandability is like some property that it has that was put there by somebody.
Nature has secrets to reveal.
I should say it's we are a part of the world and we can perceptively interact with it, and this allows us to quantify or qualify, again, whether formally or informally, the world around us. That's not a property of the world.
We can understand those secrets because being made in the image of the rational creator who made nature to manifest a rational design, our minds are attuned to the way nature was made. So there was a principle of correspondence between, as John Polkinghorne, the Cambridge physicist, used to put it, the reason within matches the reason without, the external, the reason built into nature. And that gave kind of unprecedented confidence to people in the ability to
And as far as you're aware, that didn't exist in the Greek world.
All to the same degree. And then there was a uniquely Christian contribution, which was the idea, and this was coming into vogue in the late medieval period with Catholic philosophers, and also during the period of the Reformation. And that was this recovery of the doctrine of creation, as opposed to sort of the Greek notion of an internal logos. And with that came the idea of what's called contingency, that nature, there is an order in nature. The Greeks believed in an order in nature, and that it could be understood, but they believed that the order derived from this common source of all things, this logos, and so that it could be understood essentially deductively. Whereas in the period of the scientific revolution, with the idea of a creation that was dependent on the will of an external creator who had a mind, who could have chosen to do things otherwise, we couldn't deduce what nature must be like. We had to go out and look and see. Robert Boyle said it is not the job of the natural philosopher to say what God must have done, but rather to go and look and see what he did do. And there was actually a papal.
See, this is why I say that God as an explanation, I think is just really, really post hoc. It's just any way the world is just the way that God wanted it to be. And we're only saying that because the world is that way. So then it must just be the case that God wanted it to be that way. And I'm just that's not at all convincing to me.
Decree that condemned what was called necessarian theology, and there were all of these propositions that planets must move in perfect circles. Why? Because that's the most logical way for them to do. So there was a sense in which the Greek heritage had bound science to a set of what seemed to be most logical propositions, whereas there was a liberating element as the doctrine of creation began to be more well appreciated again, and this idea of contingency
to a kind of more empirical,
observational,
testable sort of way.
Which again is not to impugn the Greeks, because I
don't think that came about because people thought the world was created. Also, since he's mentioned contingency, I think it's worth specifying that at least within the context of what's often referred to as modal metaphysics, the term contingency, you'll often in common parlance hear the term contingency used interchangeably with the word dependence. Like, oh, well, whether we have the meeting today at 2 is contingent on whether Lisa gets back from her trip in enough time or something like that. That is not the way the word is used in modal metaphysics. The word contingency just refers to something that is not impossible, but is also not necessary. So we have a word for things that do not occur in any possible world. We call those impossible things. To say that something is impossible is to say that it does not obtain in any possible world. To say that something is necessary is to say that it obtains in all possible worlds. And then to say that something is contingent is just to say that it obtains only in some possible worlds. So it doesn't obtain in no possible worlds. It's not impossible. But it doesn't obtain in all possible worlds. It's not necessary. It obtains in some possible worlds. It's contingent. So at least within the framework of modal metaphysics and modality, contingency is not a synonym for dependence. It is a term that describes what sort of, you might say, sits in between impossibility and necessity. And I think that is a point worth clarifying.
I think they were just the most enlightened of the ancient peoples, but there was something that they were missing that the Judeo-Christian view, I think, helped, but that the Judeo-Christian view brought, that helped to liberate an empirical science. And many historians of science have.
Anything to say in response?
Well, I think that idea of contingency was there already in the ancient Greeks, because there was a notion in Lucretius, and he talks about something called the swerve. So he builds on what Anaximander said, which is that all things move according to necessity along with the order of time, which I think is an implication of something like a physical law. But what the atomists said, the ancient Greek atomists said, that there was this thing called the swerve. So basically you have roughly a deterministic universe, but the atoms do this swerve, which gives you some degree of indeterminism. So there's your contingency. So it was there in ancient Greece already. So I think
I suppose the sense I get from Steve here is more that it was really in the Christian period that this idea of that you can go out and test the universe, look at it, and rather than.
I think it was there. It was there before.
I think certainly have the notion of chance and necessity in the Greeks, but you get, starting with this university with people like Grosseteste, you get these systematic methods of interrogating nature. I know one of your points, Phil, is that you think you said that many Christians are not skeptical enough, that
And that's the problem. I just want to say one thing on
this
that.
method of isolation of variables, of what is the precursors to the method of inference to the best explanation. This was coming out of the Catholic universities in the late medieval period, University of Paris, University of Oxford, and then.
Yeah, that's because universities were initially a religious institution. That doesn't mean that like their values and mores were influencing anything.
It blossoms into very sophisticated methods of investigating and interrogating nature in this period when people are convinced, first of all, that nature is intelligible, and secondly, that
also, I think there was a lot of people within the Islamic tradition that had the same view of this sort of interrogating nature. I'm not saying how this is specific to the development of science under specifically Christianity.
Radically contingent on the will of the creator, and therefore must be investigated empirically. We can't rely simply on and so I think there's a famous Cambridge historian of science, Herbert Butterfield, who asks this. He says it's the why there, why then question. Something unique happens in Western Europe between 1500 and 1700, with roots back to 1300, so forth, that didn't happen anywhere else.
Its roots back and back and back. Look, science has contributions from all well, not all cultures, but many cultures.
Exactly.
Okay? So the Greeks, look, the torch has been passed from culture to culture. So at one point, the Greeks were probably the leading developers of science, and they made huge contributions to development of science. Right? No one wants to say that the Christian culture didn't contribute. Of course it did, right? But I reject this notion of a scientific revolution. And what's funny is that one of your colleagues, Glenn Scrivener, made this point. There wasn't a scientific revolution. There have been many scientific revolutions.
Very
or
true.
We could say there's a scientific evolution. Maybe that's a better way to put it.
Well, maybe.
Yeah, maybe, Steve.
But it sounds like, though, you're not convinced that Christianity was almost required to bring us to where we are today in terms of.
Nobody that studies the full history or philosophy of science would say that Christianity was required. That's a claim that Christians make, and there aren't good reasons to suppose that's true. At least Christianity isn't any more required than any of the other traditions that also contributed to science. And this is what they want to do. They want to like single out Christianity as, oh, well, sure, other cultures contributed, but Christianity was unique in really making science what science is. Well, that's just not true.
Think about this. Everyone could see there are irregularities in nature. You don't need to have a theological belief to say, look, there are irregularities in nature. Maybe we can understand them. That goes back thousands and thousands of years. You look at the moon and you see it has phases. You look at the stars, you see that there are patterns. You can see there are seasons by looking at the stars. Everyone can see there's structure in nature, there's patterns. So people want to investigate them. They're curious. And I think the fact that human beings are curious is actually what's driving this.
Well, but during the period of the scientific revolution, what happened was that the notion of regularity having a theological underpinning was then conjoined with the idea of the divine rationality. And the result of that was the mathematizing of those regularities. And that's a huge surge forward. And this is one of the things.
Yeah, but that mathematization largely happened because we had developed the mathematical tools to do so. A lot of that being contributed by the Hindus and by the Muslims. If you think of the word algebra or algorithm, then the symbols that we use for numbers today are Arabic numerals. So a lot of that had to do with the development of those mathematical techniques. The Christians didn't just come along and say, oh, we can use math to do science now. And they were the only ones that ever thought of that. That's just not what happened.
The things that was emphasized to me when I was working on Newton and on the Principia, or Principia, depending on how you like your Latin, right? That the Principia was a theological project, that Newton was trying to explicate the divine rationality in precise mathematical form as a way of giving glory to God, and also giving and illuminating nature. And so I think something there and we're probably not going to come to agreement on this, but I've got 3 chapters on this in the book, and I think I don't deny that there were preceding contributions from other culture, but something really unique and revolutionary happened in Western Europe during
See, we're always told that something, and this is the second time he said it, oh, well, something unique happened in Western Europe with the rise of Christianity with regards to the development. Okay, what was the unique thing that happened? Because the stuff that he's listed, Phil and myself have responded and shown, well, no, it's not strictly true that Christianity is unique here in this respect or in that respect. There's a number of cultures that contributed in very similar ways. So what is it that was so unique that we keep hearing about?
During that period of time, and it resulted in both the conjoining of mathematics to the regularities, in the development of very systematic methods of interrogating nature, these methods of isolating variables, and a revolutionary advance in understanding. There was.
We could keep going.
Can I just say one last thing?
One last thing, and then we'll.
All right,
Happy to give you the last word.
Okay, no, you can have the last word. 5. There's just something I've got to go off my chest. The mathematics was used because the mathematics had been developed over thousands of years. So it's really hard to do calculations without using the number system that we have. That came from the Indians. Let's give them some credit, right? The algebra came from the Arabs. Let's give them some credit, right? So more importantly, I think we shouldn't underestimate the importance of contingency. The fact that I agree, maybe we shouldn't use the word scientific revolution, but there certainly was a very significant development that happened in the 17th century. Okay. I think a lot of that is just chance and accident. One of the most important things that happened in the 17th century was the invention of the telescope, because what that did was it enabled scientists to compare ancient dogmas with actual empirical observations in a way that could never have been done before. The telescope, by all accounts, was invented by an accident. People just noticed, oh, if we put these lenses together, we start magnifying things, and not just a telescope, the microscope too, because then we started to understand, oh my God, there's this whole hidden world of bacterial diseases.
Sure.
So there's so much contingency involved here.
And we'll leave it there.
Yeah,
I suspect Stephen would just
I have
the
things to say
empirical
about that
method.
too,
The
but that's fine.
empirical method is sort of.
I think we can
behind
agree
but-
that there, especially in that period of history, there was not a conflict between science and religion, and that therefore there is no intrinsic or long-standing perpetual conflict between.
I mean, yeah, there probably was, considering a lot of what science was discovering throughout the 16th and 17th centuries ran recalcitrant to what a lot of theological teachings were, such as, Earth's position in the solar system. So yeah, I think that during this time there certainly were conflicts between what we were learning through science and what various theological traditions were teaching.
Between science and religion as the Draper
But we're about to start really getting into the meat of the discussion here, so I hope you all are ready.
and white folks have said, right?
That at least is a point of commonality. Okay. Hi there. If you science, the newsletter, literally Big Bang Cosmology, and it might be helpful just to again reiterate, Steve, that in your book, Return of the God Hypothesis.
Let's hold both books up, shall we?
Why don't we? Return of the God Hypothesis. There are these 3 specific major scientific discoveries that you're talking about from the past century, which for you point back towards the idea of a divine creator. The first of which you tackle is Big Bang Cosmology, this idea that the universe had a beginning. So this is going to be our first major point of discussion. Perhaps you'd like to start by sketching out your case here for the way in which cosmology has pointed towards an origins event for the universe, and why you believe this lends evidence to the idea of a God.
Yeah, sure. Phase 1 of the argument, okay. If the argument is predicated on the evidence that we have of a beginning, that there are several very key discoveries from observational astronomy that have pointed back to a beginning point. You have the redshift data from astronomy showing that the universe appears to be expanding outward. If you back extrapolate that expansion, you get to a point of convergence where you can't back extrapolate any further, suggesting a starting point for the expansion and arguably the universe itself. There are other evidences from observational astronomy that have reinforced that. Things like the cosmic background radiation that was first discovered in the 1960s with Penzias and Wilson, the subsequent discoveries of COBE satellite, showing that the kind of perturbations you would expect on a Big Bang model were also present in those, in the background radiation. And then further, there's a whole host of other empirical observations about the ages of galaxies and so forth that fit with the idea of a beginning point. In the book, I also point out that there are developments in theoretical physics, the singularity theorems of Hawking and Penrose, and the BGV theorem of Borde, Guth, and Vilenkin, that in one case I think provides a proof, in another case a strong indicator of a beginning. The thing about something in theoretical physics or attempts to make proofs is they're always predicated on certain assumptions or conditions. In the podcast, Phil, you did with Sir Roger Penrose, who's honored to be mentioned, even if it was in the mode of a critique, just to make sure we're understanding each other. He critiqued me for not describing the conditions under which the singularity theorems would apply. I have an extensive.
So what I want to say here is just that all of the things that Stephen has listed here, the redshift and the expansion of space, the cosmic microwave background, these don't, you can make them consistent with a view where the universe has some sort of absolute beginning, but they don't in and of themselves imply that as an answer. What they do imply is that very, very early in the universe's evolutionary history, it was in a very, very hot and very, very dense state, very energetic, and that it has evolved from that state, and that the kind of universe that we see today is exactly what we would expect for a universe that has evolved from an extremely energetic, extremely hot, dense state very, very early in its history. But there are a variety of models and a variety of ideas about how you can extend that, not even necessarily indefinitely into the past, although that is an option, but just before these earliest moments that we currently know about. So the things that he said there don't immediately indicate that the universe has an absolute beginning. They're consistent with that idea, but they don't immediately indicate it.
Extensive discussion of that, the weak and strong energy conditions, the whole issue of quantum gravity inside the Planck unit. So I'm well aware of those limitations on the proof. So my conclusion about the singularity theorem was not that it provided an absolute proof, but a strong pointer to a beginning. And it's actually kind of worth, I think, remembering what Hawking was thinking about when he first proposed this, that Hawking was doing was doing black hole.
Also, the singularity theorems suppose classical general relativity, and they don't really indicate that the universe would have a beginning. All they indicate is that there's some point where the mathematics of general relativity stops providing any sort of meaningful answers. I mean, that's about it. You reach a point where general relativity is no longer a consistent theory for describing what's happening at the particular energy scales.
Black hole physics at Cambridge. He's a PhD student, and he's aware that in general relativity, massive bodies cause the curvature of space. So he's thinking about the evidence for the expanding universe, and he realizes that as you go in the forward direction of time, matter is going to get more and more and more diffuse. But then if he winds that backwards, that as the matter gets more and more densely concentrated in the reverse direction of time, then you'll get a tighter and tighter and tighter curvature, going back to some limiting case, some point in the past where you can't get any more tightly curved. Now, we can, and we'll discuss this because, as I said, I'm well aware of the limitation on that proof is that when you get small enough, quantum effects become very important, and the depiction of matter is no longer as I'm going to say his name again. Naesh explains this very well. That you have we no longer
Naesh Afshori, I believe,
conceive of matter as spatially discrete, but it's a wavicle. It's spatially extended and it's a particle at the same time. And so we don't really know if you're going to get continued curvature, but when you get to that point, you're inside the Planck unit, which is 10 to the minus 43rd of a second, or as Hawking and Ellis pointed out in their 1972 book, you're inside 10 to the minus 33rd of a centimeter of space. And in that first book, they
10
said,
to the negative
well,
35.
that's not an absolute singularity,
I think it's
but
10 to the negative 35
for all
meters.
intents and purposes, a singularity. So I'm in my development of the case, I want to say that's a very strong indicator as to what was going on in the past, that we're going back to a beginning point of some kind.
Now, that is correct. Everything that Stephen said there is correct, that this is a strong indicator for the universe, again, very early in its history, being a very, very hot, very energetic, very dense state. But it doesn't say that this has to be where everything started, that this has to be some absolute beginning. We don't know if there is such a thing or not. I probably lean towards the idea that there is, but I could very well be wrong about that.
And then I think the Borg-Vilenkin theorem provides additional support for that based on special relativity. It's not subject to the same condition. There are other conditions that are important, and some of these pre-Big Bang models provide model-specific exceptions or exemptions to the BGV theorem. But I think on balance, it too is providing epistemic support for a beginning.
I think it's worth pointing out that the Borg-Vilenkin theorem is not a theorem about the origin of the universe and does not say or suggest that there is one.
That's part one of my argument. The part two,
and even if there was, it doesn't tell us anything about that. That's not what the BGV theorem does.
Well, let's just try and bring this into a summary.
Well, here's the big point about that.
Go ahead.
If you have a beginning,
you have a beginning.
Okay, and if we're going to any argument predicated on a beginning is going to create difficulties for a materialistic worldview, because
I do not. That. What's the argument for that? I think that a naturalist can grant that that there's some sort of absolute beginning. That's not in and of itself immediately a problem for a naturalist worldview.
Because either before the beginning, which we have to put in scare quotes because time is beginning, or independent of the beginning in an ontological sense, there is nothing materialistic to do the causing, because what is beginning is matter, energy, space, and time. So
yeah, but on a naturalist view, where the naturalist takes that there is some absolute beginning, all they're going to say is that there is just some initial moment, but it is not itself caused. It wouldn't make sense to say that first moment was caused by something else, because then that something else would just be the first moment. And then what caused that? So there's some first moment. It wasn't caused by anything. It doesn't make sense to say that it was caused by anything. It's just that wouldn't be the right way to look at it from a naturalist perspective.
So on a straightforward conclusion based on observational astronomy, and I think the most straightforward reading of these proofs from theoretical physics, I think you have not a proof, but strong evidence of a beginning, and that poses a problem for materialism, an explanatory challenge for materialism that it can't meet, that theism can meet, because
I don't think it exposes an explanatory problem either. Somebody is either going to think that this initial state is just physically necessary, or they might think it's just brutally contingent. And if the first one serves as an explanation in virtue of the necessity, and the second one is just suggesting that there simply is no explanation to be given. It's not avoiding one. It's not trying to get out of giving one. It's saying there just isn't one to give at all.
Because if you posit an independent entity who transcends matter, space, and time, and also has powers of volition, you have the necessary conditions of an adequate explanation, causal explanation for the origin of the universe if it had a beginning.
Okay. So just before I bring Phil in to start to push back on this, just in summary, your view is that looking at what you might call, as far as you can see it, consensus view on cosmology.
Not so much consensus, but more of a prima facie case based on observational evidence,
on what we know
and theoretical physics.
Observational evidence of the universe that appears to show, if you wound the clock back, you would get to this very hot, dense state in the past, and what appears to be a beginning moment. You likewise add in the Borg-Vilenkin theorem, singularity theorems that Penrose and others formulated, And there's a lot of different strands that point back to the idea that there is
Exactly.
a beginning.
Yeah, it's as I concluded at the end of the chapter on this, the 6th chapter of my book, as best we can tell, there was a beginning.
As
But
best we can tell.
acknowledging that there are loopholes that could be
And we'll explore some
Yeah.
of those.
Yeah.
But the reason that this gives us evidence for a creator outside of the universe is because you have to posit something like that when what you're talking about coming into existence essentially is matter, time, space, and energy. You have.
But here's the problem. Even if you grant that there is some initial moment, it's that this isn't an event where the universe springs into being. That's not what happens. It's just, it would be like saying that the North Pole is where the Earth comes into being. That just misunderstands what's being talked about. Just completely misunderstands what the Earth is. The North Pole, you could argue this equally with the South Pole, but the North Pole is just sort of a point of convergence where you might say all points on the surface of the Earth can converge onto the North Pole. But the North Pole isn't an event where the universe was or where the Earth was caused to spring or come into being literally from nothing in some like ex nihilo way. It's just a point of convergence. It's just sort of this initial point where everything you can't go past. There's no such thing as a past to that. So I think granting that there's some sort of absolute beginning for the universe, saying something along the lines of this is a moment where it comes into being is just using entirely the wrong language.
You have to have something that, in a sense, transcends those categories, and this appears to be the God. Therefore, is
right. And I think one of the interesting things about the alternative cosmological models is that they always have to posit something that is separate from or transcendent from the observable universe we have. It may be a prior mathematical state, as in quantum cosmology, or it might be a prior Big Bang. But transcendence in the strict sense of the word as something separate from seems, I think, by all concerned to be something conceded as a necessary condition of explanation. Causes need to be separate from the effects that they produce.
Okay.
I'm not sure what he means by transcendent here, nor what's really being said when he says that causes need to be separate from their effects. I don't know what exactly that's supposed to mean. I mean, if it's just saying something like causes need to, number one, both precede their effects in time, and number two, have sufficient power to produce their effects, then sure. But I don't know if that's what he's saying there. That was kind of confusing to me.
Okay. Phil.
Okay, so let's just take a step back and talk about the broader conversation here about the Big Bang and the beginning. What's often happening is that there's a bit of a bait and switch going on.
Okay.
In particular, two notions of the Big Bang are getting confused. So in our book, we talk about one definition of the Big Bang, which we call the hot Big Bang. And that says that's a theory, if you like, that says the universe evolved from an incredibly hot, dense state. And that theory says nothing at all about what came before that. It doesn't say whether there was a beginning of time or not. It just says the universe evolved from a hot, dense state. The other definition that we talk about for the Big Bang is the Big Bang singularity. So the universe evolved from a singular state. What we mean here is that the curvature, the pressure, the density goes to infinity. This is the sort of beginning of time, if you like. Now, all the observational evidence only tells us that there was a hot, dense state. It doesn't say there was a singularity. In fact, I would say there is no evidence at all that says, not any empirical evidence that says there was a singularity. In fact, you can't really get any empirical evidence for a singularity. It doesn't make any predictions. And in fact, there's something called the cosmic censorship conjecture, which I think is very plausible, that says actually singularities are hidden behind horizons. And in fact, if you could see a singularity, you would actually have a breakdown of causality, which would threaten the Kalam in the other way. It would threaten the causal principle, perhaps. So we can't see singularities. There's no observational evidence for them. And in fact, we did a survey of physicists, and I've done 2 surveys.
So before he talks about the survey, this is how this is viewed in modern cosmology, what Phil is talking about. When cosmologists are talking about the Big Bang, they're talking about the hot Big Bang phase of the universe's evolution. And there is a before that. and that is inflation. Now, some cosmologists will say, yeah, well, we don't really know that inflation happened, and we don't know that inflation happened, but there are certain observations we can make about reality that are very, very difficult to explain without something like inflation having happened very, 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 very early in the universe's evolution. And at least in standard lambda CDM cosmology, inflation is understood as something that happens prior to the Big Bang. That the hot Big Bang phase was sort of set up by inflation, that this is the reheating epoch that occurs immediately after the inflationary epoch. And Phil is also right that this notion of an initial cosmological singularity is not a part of standard lambda CDM cosmology. Most cosmologists don't think that there was an initial cosmological singularity, even if they think that there was maybe some sort of absolute beginning. Most physicists don't think singularities are physically real objects in the first place. They think they're what you get when your mathematics is no longer, your physical theories are no longer capable of providing meaningful descriptions of the energy scales you're trying to subject them to.
Surveys now. And this is very important. We asked, so the first one we did was a survey, was at a conference organized by the Niels Bohr Institute in Copenhagen, and it had leading physicists there in theoretical physics and astronomy, cosmology, astrophysics, numerical relativity, and it had top people. And we asked them various questions and controversies within physics. We asked them, I think it was 12 questions, things like, what you think is the best candidate for dark matter, for dark energy? And the only question that we got a majority view on anything on was that the Big Bang should only be understood as the hot Big Bang, not as a Big Bang singularity. So when physicists say we've got evidence from the cosmic microwave background and the redshift and blah, 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 they're only saying the hot Big Bang. Okay. So this is not empirical evidence of a beginning of the universe.
Wrong button. And that's what I had mentioned earlier, is that none of this is evidence for an absolute beginning. It's evidence for the universe being in a very, very energetic, very dense, very hot state very early in its history. Could that be a beginning, an absolute beginning? Yeah, but the data we currently have does not itself immediately suggest that. You have to sort of parse that out of the data that we have by considering a variety of other metaphysical or philosophical assumptions with respect to your interpretation of the data as it stands. But the data itself does not suggest that.
The universe. Okay. Now, in fact, I would challenge Stephen, what empirical evidence could you possibly have of a singularity? I just can't see how.
Should we
Yeah.
pass that back then? So the hot Big Bang is not evidence of a beginning, and the singularity theorem itself is contested, says
well, we'll come on to that. It's more like we couldn't observe a singularity if there was one.
Well, of course, that's where the laws of physics would break down. I'm not disputing that. The point is that the back extrapolation that's been involved in inferring the hot Big Bang state takes you.
That's done utilizing general relativity primarily. Like, that's why it all goes back to a singularity when you do this, is because your curvature, your density, all that becomes infinite. But we know that general relativity, classical general relativity as it stands today, does not apply at such very small scales and size scales and very, very high energy scales because of the introduction of quantum effects. And we do not yet have a theory of quantum gravity, so we can't really speak about these very earliest moments, at least with respect to where we are in the universe's evolution, these very earliest moments, until we have such a theory, and we just currently don't. So the fact that we can back extrapolate to a point and then all of a sudden we reach like a wall, we sort of hit a wall, is not because there must be a beginning there. It's because our theories are no longer adequate at these energy scales. We need better physics, and we don't currently have it.
Takes you back to a point of convergence past which you cannot go. And that's a consequence of the redshift as much as it is the consequence of the singularity of Hawking and Penrose, the singularity theorems. The point that I'm making is that it's a reasonable conclusion to believe that the universe had a beginning. There's no way of getting beyond that hot Big Bang.
I think that you can make that conclusion but you can't you can't make that conclusion based only off of the scientific data that we have or the empirical data that we have. You have to take that plus a variety of other philosophical assumptions. In the case of like Stephen and many others, are going to be a variety of theological assumptions that they have that is then going to inform, oh, this is probably some sort of absolute beginning. But again, the empirical data in and of itself does not indicate that.
To something before. This is something that in the book, I'm stumbling again over his name. Meyer he agrees with William Lane Craig that there's no evidence for a beginningless universe.
But we also said there's no evidence for a beginning.
No. There's a
that is true. There is no evidence for what the beginning of the universe, empirical evidence for what the beginning of the universe is like at all, if there is one. There is no evidence that there is one. There is no evidence that there isn't one. We don't have the models to give us that. We don't have the tools and the technology to understand that yet. So this goes both ways.
Difference between evidence and proof, and I think the what happens throughout your book is that there's an absolute 100% standard of proof required for anyone who wants to say that the universe had a beginning.
That's not what we're talking about.
And well, that's what the singular to suspend the Borde-Guth-Vilenkin theorem simply because there are models that could circumvent its conditions.
But the conditions of the BGV theorem don't indicate that the universe had a beginning. All they tell us is that inflation is bounded in the past, in the past null time-like geodesics, past-directed null and time-like geodesics. That inflation has some past boundary, but the universe isn't inflation. Inflation is a process that occurs on space in the universe. So the universe might be doing a whole host of things prior to its inflationary state. But there is a past boundary to specifically the inflationary state. That doesn't tell us whether the universe has a beginning, as both Guth and Vilenkin themselves have clarified.
Is to require an absolute proof.
No, it's not. It isn't. It just isn't. It does. We're not looking for an absolute proof. That's just not
I'm saying that there's evidence of a beginning because the back extrapolation.
Can we agree there's no empirical evidence for a singularity?
Well, you wouldn't get an empirical.
Right. So
singularity is an artifact of mathemational physics.
So let's find the common ground. Yep. We agree.
Right, but that's a red herring because no one has ever said that.
Well, so let me just get this.
The singularity has a technical definition in physics, which is a place where the laws of physics break down. You wouldn't get. There's no possibility of empirical evidence of a singularity. But it's a
hypothesis based on extrapolating the mathematics.
Conjoined with general relativity that would lead you to think that you're getting to a singularity or a near singularity. But I'd like not to get hung up on.
Yeah, can I come?
Well, just so that I can understand the empirical evidence we do have from cosmic microwave background radiation, redshift, and so on. You're saying that all that gets you is a hot dense state, not a beginning. But you're saying that you think it's consistent with and lends evidence towards the idea of a beginning.
Because and there have been,
when you join
I don't
with,
know what their survey has shown, but
and so on.
I first encountered this with a very compelling talk by Alan Sandage, Robert Jastrow. Many of the physicists who were first articulating the case for the Big Bang thought it clearly pointed to a beginning. And so
okay, well let's pass it back to Phil now.
Where we're getting confused is the difference between evidence for something and an absolute 100% certain proof, which is
and this is asking for that. That's just
no. So you're keen to say we're looking for an inference.
Yeah, I don't think Phil has at any point here said or suggested that we need some sort of absolute proof. Look, if on a general definition of evidence that most philosophers, including philosophers of science, are going to work with. Evidence is something that's expected, given to say that something is evidence for a hypothesis is just to say that it's an observation or what have you that's expected given the hypothesis, and that if you did see it would raise the probability of the truth of that hypothesis. The universe being very, very hot, very, very dense, and very, very early in its history is minimally evidence for a beginning, but it's not enough to say that, oh yeah, we can argue that point, because it's also consistent with there being a hot dense state that evolves from some previous state as well. So, and the thing is, that state could be the beginning, and all that would mean is that the hot dense state isn't. What came before the hot dense state is. So it's very minimally evidence for a beginning, really only in the sense that it is minimally expected given a beginning, but it doesn't meaningfully raise that probability. It's certainly not enough for anybody to say that we have good reason to suppose that the universe has some sort of absolute beginning.
Inference to the best explanation, not necessarily this 100% deductive proof, but
science doesn't give you deductive proof.
No, it doesn't, and
Yeah.
we're not
Okay,
asking for it.
So,
I
so
mean,
go
it's
ahead.
just-
Go ahead.
Well, it seems like you are, though. That's
No,
what-
absolutely not.
I don't know how it seems like he is. I'm trying to figure out. I know what I want to say. I'm trying to figure out how I want to word this, because I want to be charitable. But I feel like what Stephen is doing something a little dishonest here, where Stephen has presented a case that he thinks serves as evidence for there being an absolute beginning, and Phil has quite elegantly explicated that this is not actually at least even remotely strong evidence, if evidence at all, for there being an absolute beginning to the universe. And then Stephen is sort of countering that by saying, oh, well, you're just demanding some sort of proof. No, he's not demanding proof. He's just saying that you haven't met a reasonable standard of evidence for the claims you're making, because what we have just from the empirical data itself is consistent with there being a beginning, which Phil has conceded, but it's also consistent with there not being a beginning and there being something prior to the hot dense state that set the hot dense state up, which we already know exists, and that was inflation. So I kind of feel like that's just a little bit dishonest on Stephen's part to say that Phil is implying that there needs to be some absolute proof or something like that. I don't think he's doing that at all.
You believe, obviously, Steve's mischaracterizing you.
Yeah, it's just not. We're not asking for 100% proof. No, okay. What we're asking for is an understanding of physics that we don't have at the moment. Okay, so basically, what these singularity theorems prove is that the space-time that obeys the condition of the theorem encounters a singularity. But it doesn't say there isn't some other space-time that doesn't obey the condition of the theorem. So now you have to ask, well, what are the assumptions in the theorem? Are they trustworthy? Because if they're not trustworthy, the conclusion isn't trustworthy. And what I think there's very broad consensus on in physics is that the conclusions are not trustworthy. In fact, right, the people that invented them, Penrose, Hawking, Ellis, Garock, they I think
they have abandoned them.
They've abandoned them, right? Not as they haven't abandoned in terms of the mathematics is good mathematics, right? No one's saying that the maths is wrong, right? The question is, for any physical theory, you have physical assumptions.
Holy fucking shit, I am muted. Okay, thank you for that. I love you guys. I paused this at exactly the right moment. Phil is absolutely correct. The assumptions. And as I understand it, remember, I'm not an expert, as I maintain a lot. I at least like to think that I know my physics, but I'm not an expert. As I understand it, the Penrose-Hawking singularity theorems rely on classical general relativity. So if that's the case, and we know that classically general relativity doesn't hold, it gives way to a deeper, more underlying theory that includes a variety of quantum effects, then those singularity theorems are probably wrong. Now, there have been people who have suggested that utilizing some new information from things like black hole thermodynamics and the statistical mechanics of black holes, that we can formulate a quantum singularity theorem. I've really only looked at some of the papers on that. I haven't really looked into it very deeply. And if and when I do, there's some people that I want to talk to that know vastly more than I do. about that so that I can be sure that I understand it correctly. But I do know that it's not like a super popular, like it's talked about, like there's some physicists that have proposed this, but that it's not super popular, and that at least currently the consensus amongst the relevant cosmologists is that singularities are not physically real. The singularity theorems probably do not hold in the quantum regime, and we need a theory that incorporates those quantum effects to have a better understanding, both of what's going on with black holes, but also what's going on in the very, very early universe.
So the question is, are the assumptions trustworthy? Now, there are various assumptions. We go through them in the book. I'm not going to go through them all here, but I'll pick the one that I think is the most important. And that is that Einstein's theory of gravity describes the universe at all scales. And that is an assumption that almost, I think, most cosmologists would say is wrong, right? It's wrong because there's a contradiction between relativity and quantum
mechanics, of course.
Right?
Yeah.
So they contradict each other, right? Now, for the most part, we can ignore that, right? The quantum effects are very big, things are tiny. So we just ignore it. It's fine. It doesn't matter. But at the Big Bang, it does matter, right? Because here
in this Planck unit of time,
when you get
oh, the whites. When will the whites learn how to pronounce names? Planck, not Planck. Planck, Max Planck. Yeah.
When you get to when the
and Phil rightfully corrects Stephen later when Stephen keeps saying Borde Guth-Vilenkin theorem, and it's Borde Guth-Vilenkin theorem.
Universe is incredibly hot and dense. You're going to have to bring in quantum mechanics, right? That's the broad consensus view. There are a few exceptions, right? Penrose actually thinks you don't need quantum mechanics, but nevertheless, he challenges one of the other assumptions of his own theorem, and his assumption is that you can measure. You have to assume there's 3 space dimensions, 1 time dimension, which you can measure with rulers and clocks. And he's saying you couldn't build a ruler or clock in the early universe. So actually, out with the singularity theorem. But let's put that to one side. The main one is this quantum gravity issue. We want to combine general relativity with quantum mechanics, and until we do that, we can't believe what the theory is telling us. Now, have we done that? Not successfully. I mean, there are proposals. There's string theory, there's loop quantum gravity, there's causal sets, there's asymptotic safety.
There's quantum cosmology.
Blah, blah, blah.
Yeah.
Right. So but even if all of those are wrong, until we get that theory, we just don't know. Right. So it's not that we don't have the final proof. We're not saying we need this 100% tight, deductive proof. No, science doesn't work that way. What we're saying is the theorems just can't be trusted, full stop. Because they need this quantum gravity theory.
And this is where I would
have.
disagree, Phil. I think they're pointing to.
Well, they can't be trusted. What physicists mean by that is that the current standing of our best physical theories about how the world works do not work as they currently stand. Once we start getting to these very, very, very early moments in the universe's evolution, they just don't. They stop working. We can't get answers that make sense out of our current physical theories when we apply them at those energy scales. We can't do it. This is also the case in like quantum field theory. Past a certain energy, the mathematics just gives you gobbledygook. So physicists invented a way to say, well, let's just not do that. And we call it effective field theory. All of our physical theories they break once you reach certain energy scales. They don't work at those energy scales. This is not controversial in physics. And as a result of that, there is an extent to which once we start approaching certain energy scales, we can't rely as much on our physical theories and what they tell us as we would like to, because of the fact that they break down when we start to approach those scales. We need better physics, and we don't have that yet. And until we get that, we can't make definitive statements or really even confident statements about whether or not the universe has some sort of absolute beginning, which there are cosmologists who think, yeah, maybe it does, or whether it extends indefinitely into the past in some way, shape, or form, or whether saying something like has an absolute beginning or extends indefinitely into the past are meaningful statements to make. We might discover that these kinds of questions don't really make sense.
To something, and Borguth-Vilenkin, which is not based on as restrictive conditions, I think points more decisively in that direction. But the other part of my argument is that if you decide you don't want to depict the beginning of the universe classically in general relativistic terms, as it were, and you invoke a pre-Planck time quantum description of the universe, you invariably get a universe that is depicted as a superposition of essentially possible states of affairs, possible gravitational fields with different configurations of space and matter within those fields. And the depiction is essentially not materialistic, it's mathematical. It's a depiction of possible states. And Vilenkin has pointed out that this is very odd because you have this whole mathematical apparatus that precedes the beginning of the universe in quantum cosmology, which is taking into account the limitations of the singularity theorems, the conditions that have to be met. It says we need a theory of quantum gravity. And you end up with a system that has a big hairy equation, the Wheeler-DeWitt equation, that needs to be solved to give us a universal wave function. And the idea is that if the universal wave function includes among the possible states of affairs in superposition a universe like ours, it will then constitute an explanation of the origin of the universe. But that mathematical apparatus that precedes the origin of the universe is mathematical, it's conceptual. So,
well, the math is, but the thing with that is, well, number one, the Wheeler-DeWitt equation is used a lot in quantum cosmology, but it's not like you have to have that as a part of your approach. I probably couldn't explain. The Wheeler-DeWitt equation is, I don't know if it would be correct to call it a sort of equation of motion, but I know it's important when understanding quantum cosmology. But there are approaches that don't use it. But also, a lot of people who take that kind of approach are going to think that this universal wave function is a physically real, like a concrete thing. So they wouldn't think that it's just mathematical.
So what Vilenkin has noticed is that he says, before there's matter, space, time, and energy, what tablet could these laws referring to that whole apparatus be written on? He said, if math is the domain of the mind, are we actually saying that the universe has come out of mind? And what I'm arguing is that when the straightforward Kalam argument rendered, however, whether as an inference to the best explanation or as a deductive argument, is circumvented by alternative models of cosmology, and I think every one of the ones you discuss reveals this, that something is affirmed in those models that has its own theistic implications. In particular, unexplained fine-tuning, or in quantum cosmology, the big hairy equation that has to be solved, the Wheeler-DeWitt equation, is solved by the physicists making arbitrary choices of the boundary constraints they're going to apply to the equation in order to get a universal wave function out that includes a universe like ours. It's a teleological modeling where there's an information input by the physicist into the mathematical apparatus to get a wave function out that will provide an explanation of the origin of the universe. Well, that's intelligent design. They're modeling the input of information into a mathematical apparatus to model how the universe could have come into existence. And you find this in the Steinhardt model, not the same kind of thing, but these unexplained inputs of information or fine-tuning in all the attempts to circumvent the beginning. So yes, you can get around the beginning, but at an epistemic cost to naturalism. And that is always the affirmation of unexplained fine-tuning and often some very, very wonky physics, which is why you're correct to say.
But if the fine-tuning is just of the physical theories, okay, then we fine-tune our physical theories to better describe the world. That doesn't imply that the world is finely tuned. That just implies that we probably have incomplete theories.
To say that you're probably right. Most of the 25 models are not going to be correct.
Okay, so there's a lot of information there. All right, so
there's a lot there.
There's a lot
to go through them one by one.
Okay, let me.
The point I'm making is I'm not hanging the whole of my argument on the evidence for beginning, but I think we've been far too diffident about seeing what the gravamen of the body of evidence is showing, that it's pointing strongly in that direction. But if you don't like the beginning and you circumvent it with a quantum cosmology or a conformal cosmology or any of the others discussed in the book, you invariably have an epistemic cost.
Okay. So if I could attempt my layman's summary, and feel free to correct me on this, yes, there are other models, and you represent a number.
By the way, I think this is a good time to point out what I said earlier when the stream started, that I think Stephen Meyer's a more formidable than he's given credit for. I mean, you just listen to everything that he just said. Yeah, it wasn't. So, I mean, a lot of it was, in fact, correct. Like a lot of what he said about the Wheeler-DeWitt equation and this approach and how physicists use this to approach understanding the universe with respect to quantum cosmology is correct. Not everything that he said I don't think was correct, but this is not something that your typical run-of-the-mill apologist really talks about. So, I think Stephen Meyer is a bit more formidable than people give him credit for.
Number of them in the book that don't necessarily point to a beginning, but each of them comes at a cost, says Stephen, in terms of there being some other payoff, which in his view do have some kind of theistic interpretation. And in the end, particularly those that invoke a kind of a mathematical kind of solution to some of these issues are kind of inferring some kind of information input from the outset.
They require it. They require it as a condition of explanation.
Yeah.
And
all
so
of our physical theories,
whichever way you look at it, there's going to be something pointing back to the God conclusion as far as Steve is concerned. Okay, where do you want to begin?
There's so many topics that Stephen's raised there. So, and I want to try and cover them all. So you'll have to bring me back if I forget one or another. So I want to go back. So first off, he quoted Alex Valenkin, and I think that's a misquote, because Alex Valenkin doesn't believe in a God, right? He believes that the universe does have a beginning, but it doesn't need a cause. Right. Okay, so he has this. He does mention, like, where could the laws of physics be written? I think that was honestly a bit of a
turn of phrase.
It's a turn of phrase. Well,
I thought it was an insightful rhetorical question.
Hang on. I think
never claimed that he believed in God.
Okay,
nor does my argument depend on what he.
Right, let's make that clear, because when you have that comment, it sort of hints at, oh, he's thinking there's a mind. He's not thinking that. In fact, if you read his book, Many Worlds in One, is incredibly anti all of the arguments that Stephen and other theists put forward. He basically, although he thinks the universe had a beginning, he doesn't think it needs a cause. So out with the calm. He also thinks, like, the multiverse is real and solves fine-tuning, so out with the fine-tuning argument. And people often quote Alex Valenkin and don't quote this fact. It just seems incredibly unfair.
You feel it's a bit selective.
Yeah, it is. Now, hang on, Stephen. I didn't interrupt you, right?
Let's go.
Okay, now, let's talk about the Border-Guth-Valenkin theorem. What I've actually sat in Guth's office and Valenkin's office and asked them about this, right? First off, I can say, and I think maybe we can clear this up, that it's pronounced border, not board. Okay, everyone seems to pronounce right. I got that from Alan Guth, and I think he knows how to pronounce his colleague's name. Okay, so if I slip up and say board or borde, please correct me. So, okay, what does this theorem say? Okay, it just basically what was going on is that they came up with this theory called inflation. So Alan Guth came up with this theory called inflation, which has this accelerated expansion
in the very early moments of the universe.
This
inflationary period.
And it was thought by Valenkin, actually, he was one of the pioneers of this, to be eternal into the future. So once inflation starts, it never stops. It makes universe after universe after universe. So it's eternal. So they asked the question, well, if it's eternal into the future, can it be eternal into the past? And their conclusion was, no, it cannot be eternal into the past. So inflation requires a beginning. What's in the paper is that there's a boundary to the inflating space. Okay. Now, first off, other people have challenged that. This is not like an agreed upon fact by everyone. There's a recent paper by Lesniewski, Davis and Essen saying actually they made a mistake, and it's actually you can have an inflating space that goes back into past. There are in other papers that have said this. Now, again, the point I want to emphasize is no empirical way to adjudicate this disagreement. Okay, if inflation happened and it's eternal, and suppose there's some beginning to eternal inflation, we are not going to see it empirically. So that puts caution on this conclusion, right? Because we want science to be empirical. This is kind of why I think we need to emphasize the uncertainty here. We're in much more uncertainty about these topics than it would appear, right? We don't know if inflation, even happened. I think there's a good case to be made for inflation, but it's not watertight. All right, it's it's reasonable. But in the book we go over a whole fights about it, for arguments for and against inflation, and I often change my mind about it every other day. It's a difficult topic, right?
Okay.
But even if inflation did have a beginning, okay, so something could have come before inflation, right? It doesn't have to be something abstract. It could just be simple. There was a collapsing universe, and then there was an expanding universe.
And this is where other models come in. There are other options on the
right,
table,
and we don't know which one is correct. So basically, we have to be agnostic about these sorts of issues, right? It's just not correct to say that these points of beginning. In fact, Alan Guth thinks the universe is eternal into the past, right? And surely Stephen knows this, right? I mean, this is very well known.
And so from your perspective, Phil, what you're dealing here is that there's lots of different people with different perspectives, some of which might indicate a beginning, but that doesn't necessarily mean a God beginning. It could be there's some other formulation which suggests there's something else happening in the quantum realm, whatever it might be.
Right. So let's just take an example. Suppose you get a collapsing universe that expands.
Right.
Okay. I don't say what on earth is immaterial about that. I mean, it seems
this doesn't have any theistic implications.
I don't know what the theistic implication is supposed to be of that. Like, why is that
right?
Showing pointing to theory. Not saying this is right.
I think this would be a good time to just to say that regardless of, like, if you believe that God exists, I don't think at the end of the day your belief in God is going to sort of hinge upon whether or not the universe truly is eternal to the past. I think that if you were to go ask William Lane Craig, if we discovered empirically that the universe is eternal into the past, would you stop believing that God exists? I think he would say no. I think that he would be like, I'd have to give up obviously the Kalam and all that, and maybe rethink about some things. But I think he would be firm in saying that no, he would not stop believing in God. And I think that most people who run a Kalam style argument would also say that, yeah, maybe not all of them, but I think most of them would say, yeah, if we did discover empirically that the universe were eternal into the past, I wouldn't stop believing in God. And I just don't think that suppose for a second that God does exist. I don't think whether or not the universe has a beginning has any bearing on that. I just don't. Also, I do want to say I really like how Phil sort of outlined the BGV theorem there, and what's really going on is that it says that inflation, the inflating region of space, has a boundary in the past. That doesn't mean the universe has to have a boundary in the past. Now, if one wants to argue that this boundary to the inflating region is an absolute beginning to space or to the universe, they can, but the BGV theorem itself does not indicate or suppose that. All it says is that there's a past boundary to the inflating region of space. It does not say that that space or that the universe must start there. And this is explicit in the paper.
Yeah,
this is one option,
but it's a plausible option among the options.
May I?
Right.
This is right on point. Okay.
Okay.
So
do you mind if we go back to Steve?
Yeah.
Well, can I answer this thing about inputting information?
Shall we come?
Okay, we'll
let's
come back
do
to
one
that.
thing at
Okay.
a time. We'll come back to information as
Right.
well. But we're on Border. Sorry,
Yeah,
Border.
Think of the border between
Thank you for
the-
eliminating
and
the
they
pronunciation.
and
pronunciation.
the inflation, and Vilenkin certainly seems to have said this implies a beginning. Although,
Well, yeah, Phil's probably going to say the same thing I'm about to. Vilenkin does not say that the BGV theorem implies a beginning, or at least that's not currently his position, and that can be proven. And I will probably do that in just a few minutes. He does believe in a beginning, but it's not because of the BGV theorem. It's just because of probably personal philosophical considerations that he has.
No, wait a minute. When I sat in Vilenkin's office, in his popular book, he said that this was a proof of the beginning.
Right.
That was in a popular book,
all right,
not in a scientific paper.
okay,
Right. And when I asked him about it years later, he backed off that claim. He said, no, it only proves that inflation had a beginning. When I asked him, he said, no, this only proves inflation had a beginning. It doesn't say that the universe had a beginning.
So we're going to distinguish between
these
inflation and the universe.
When they quote this theorem, when they quote Vilenkin, right, and they don't quote what they say now, which is that these theorems only say that inflation had a beginning, how, you know, how does that prove that the universe?
Has it switched? Yes, it has. All right.
That means that inflation must have had a beginning. It doesn't really say that the universe must have had a beginning, but it says that the universe could not have been expanding forever.
The theorem proves that inflation must have a beginning, right? The universe as a whole, the theorem doesn't say that. It says that the expansion of the universe must have a beginning.
That means that inflation must have had a beginning. It doesn't really say that the universe must have had a beginning, but it says that the universe could not have been expanding forever.
The theorem.
So, I mean, I think that kind of settles that. There you have two of the three authors explicitly saying that this theorem does not say that the universe has to have a beginning. It says that inflation as a process on space cannot be extended indefinitely into the past. You could not have inflation, according to the theorem, you could not have inflation happening from eternity past. That's what it says. You could have the universe existing past eternally in some non-inflating state. And the paper itself even says that you would need some other physics, some non-inflationary physics to describe the universe prior to the inflating region or the boundary of the inflating region. So if these authors thought that this theorem was some strong empirical theorem for an absolute beginning to the universe, why are they talking about extending our understanding of pre-inflationary physics by appealing to physics we don't currently have? By saying, oh, well, if you want to describe what happens before this, you need different physics. That doesn't sound like a sentence that would be in a theorem or in a paper outlining a theorem that supposedly shows that the universe has an absolute beginning. You'd think they'd say, yeah, this theorem shows that the universe has an absolute beginning. That's raps. But they don't say that. Why?
We've had a whole problem of taking him out of context on the other side, because I think he wrote an article in the journal Inference, edited by my colleague David Berlinski, where he was very clear. He thinks the universe probably did have a beginning, that the models that circumvent the BGV theorem are all the models that imply an eternal past are all problematic, and so on balance, yes, it's
So number one, he doesn't think the universe has a beginning because of the BGV theorem, and number two, he doesn't think that some of the models that subvert the BGV theorem fail simply because they subvert the BGV theorem. They fail for a variety of other theoretical or observational reasons.
In the strict sense, it only establishes that inflationary Big Bang had a beginning. That if the universe is on average expanding from a beginning point, you can take it back that far. There are models that obviously propose a pre-Big Bang contraction, for example, the Steinhardt model, and that is a good one to illustrate my point. Okay, because in the Steinhardt model, first of all, there have been papers come out now that Steinhardt has conceded that his model, his cyclic ectopic model, does require ekpyrotic, thank you, model also is subject to BGV. But the idea is you can't go back. The model, the BGV theorem takes you back to the point where inflation starts. What happens before that? Well, there are contracting models. There was a previous phase and the universe was contracting. In Steinhardt's work, he posits a unique field that changes the energy density of the universe from positive to negative and back again. Now, there's no other field in our knowledge of physics that does something like that. So one of the epistemic costs of these alternative cosmologies is often a gross violation of Occam's razor, in that they multiply theoretical entities, and often very imaginatively so. But in order to get the contraction phase to work just right, so it smooths out the background radiation so that you get a homogeneous background radiation in the next phase, the mathematics has to be exquisitely finely tuned. And so if you have someone who is gerrymandering the mathematics to make the model work, that is a reflection of what would need to be taking place in nature, that it would itself need to be finely.
No, that's not a reflection. The fact that we have to fine tune our models to understand the world doesn't mean that the world must also be finely tuned.
And my contention is that these alternative models to the Big Bang, the alternative models that get rid of a beginning, invariably have problems with unexplained fine tuning or inputs of information. And the pre-Big Bang contraction phase of the Steinhardt model, which is cited as one of the model-specific exemptions to BGV, is subject to that very condition that I'm talking about. So there's a robustness to the argument.
I mean, I could be wrong, but I don't. The ekpyrotic model doesn't have inflation as a part of it. So I don't know how it could be subject to the BGV theorem, which applies to inflationary spacetimes. Ekpyrotic cosmology is a different model than inflation. I don't know all that much about it though, so I could just who the fuck knows? I could just be saying gobbledygook right now.
The argument that we're developing, we're not hanging it all on the singularity proofs or the observational astronomy. I think on balance they point in that direction to a beginning. But the point is to circumvent that conclusion. Invariably, very speculative models have to be invented. That they actually have three epistemic costs. One, they usually affirm something that has theistic implications, like unexplained fine tuning.
Well, that doesn't immediately have theistic implications, number one, but number two, I would argue that if our models are fine tuned, then it's just obvious that we're the ones that finely tune them, since we're the ones that make up the models.
Secondly, they usually violate Occam's razor because there's a massive multiplication of theoretical entities. I list them all in the string inflationary model of explaining the multiverse in chapter 16, but I've seen this repeatedly in these cosmological models. And then thirdly, there's often either something completely unprecedented being asserted about how physics will work, or something that violates physics, basic physics, really well-established physics that we know. For example, Phil's co-author.
Also, just on the point of Occam's razor, this is really just sort of this principle of parsimony, that you shouldn't multiply your assumptions beyond what is needed in order to do the explaining. So that's what that means. If you need to posit more assumptions, but they also add to the explanatory power of the model, that's not really a violation of parsimony. Now, that model might not be as parsimonious as a model that explains the same things equally well with less assumptions. But the other point there is that parsimony in and of itself isn't the be-all end-all of theoretical virtues. A model might be more parsimonious. Model A might be more parsimonious than Model B in that it makes less assumptions, but Model B might have greater explanatory power or explanatory scope. It might fit better with the established precedent, with the data that we have. So it might meet a variety of other theoretical virtues, but not parsimony. So parsimony alone doesn't determine what model we should go with. It's a variety of various theoretical virtues against which we're going to judge these particular models. Parsimony just happens to be one amongst many.
There posits a return of the ether, a second dimension of time, and the speed of light is no longer constant, and goes on to say that if he is allowed to add a second dimension of time to his depiction of the universe, that may imply that causality is not a fundamental property of the universe. Well, that's a high cost to pay to formulate a model that gets around the beginning.
That's really helpful.
Well, I don't think positing that causality isn't a fundamental feature of the universe is at all a high cost. I don't think that causality is fundamental. to reality. There are some, not many, but some who would say causality isn't actually a thing at all. They're what are called causal eliminativists. They think that causality is just more the way that we talk about the world, but it isn't a thing in the world in and of itself. You know, that's just kind of how humans talk about it. But causality isn't something out there in the world to a causal eliminativist. I'm not one, but I respect the view.
Helpful. Okay, Phil, you might want to pick up on the information sort of being brought at the beginning sort of point here as well,
Okay,
as you respond to
so many points to go back. So first of all, I mean, the cyclic model of Steinhardt and Anna ES has been working on this. Let's give her some credit too. And of course, it goes back to earlier work. Ekpyrotic model, right? So
is this the collapsing?
No, there's a confusion. I think Stephen's just got confused here, right? What I was suggesting was there was a collapsing universe and an expanding universe. That does not imply a cyclic universe of Steinhardt and ES, not at all, right? It doesn't imply a cyclic universe.
I'm not sure which one you're talking about.
Well, indeed.
The point is that their model.
Yeah, but I'm not talking about their model.
Well, okay, but I'm talking about it because it illustrates my point well. Their model is a model specific, it has an exemption.
Sorry, Stephen, I didn't
DGV
interrupt
doesn't
you.
apply.
I didn't interrupt you, Stephen. So maybe if let me speak.
Okay, but regardless, so, you might want to speak.
Right, I'm not. I wasn't talking about the ekpyrotic model. What I was talking about is a collapse followed by expansion. Now, a cyclic universe of the ekpyrotic type has collapse, expansion, collapse, expansion, collapse, expansion, and to get that to work, right, there are other things that you need. I'm not talking about that. I wasn't referring to that. I didn't even mention that.
Do you concede that you need fine-tuning to get that model to work, though, in the mathematics?
That's a complicated answer. Let me sort of answer some of the points you made before going on to some other points, right?
Well, okay, just for clarification,
Stephen, maybe stop interrupting.
I just was wanting your clarification, though, for me. Which model are you talking about with the collapse contraction?
Well, there's many models that would just have a collapse and an expansion. So it's like what we would call an hourglass model. So an example of this would be, let's say, loop quantum cosmology, right? Mm-hmm. So here, what you're doing, you're not trying to circumvent the beginning. That's the wrong language, okay?
Yeah.
This is...
I don't like... Phil's exactly right there. That is the wrong language. And you'll notice that a lot of these apologists, William Lane Craig does the same thing. I think Frank Turek talks about it that way. There are some others that do that. Oh, well, these cosmologists come up with these models to subvert the idea of a beginning. No. It's that we're trying to understand how the universe works, and there being a past eternal universe, or there being some sort of pre-inflationary or pre-Big Bang state, falls out of a lot of these models. Like that's just the way the models are. It's not that people are creating models specifically to get around that everybody knows secretly that there's a beginning, and they're trying to come up with models to get around it. That's just not what's happening.
A lot of theists think that what cosmologists are trying to do, they know about the Kalam cosmological argument, and it proves God's existence, and they're trying to find a way around it. No, okay? Most cosmologists probably never heard of the Kalam cosmological argument. They don't care about any of these conversations. What they're trying to do is to extend the border of our knowledge, okay? So we get to the Big Bang, and that's where our understanding stops, okay? But they want to push beyond it. So what they want to do is say, okay, let's develop quantum theories of gravity and apply them to the Big Bang, and let's just see what happens. So I interviewed the people that worked on, let's say, loop quantum cosmology as an example, right? And what they did was they developed the theory over like decades before ever applying it to the Big Bang. Once they felt they had enough understanding of the theory that they could start to do this, then they applied it to the Big Bang. And what did they find? That the Big Bang becomes a big bounce. And there's a reason for this, because in the theory, you find that space has a maximum capacity. So think of a sponge, okay? You pour water on a sponge, the sponge absorbs the water. In a similar way, space can absorb energy as you start to compress it. But what happens is, as the water gets poured on the sponge, eventually the sponge gets filled up. It can no longer absorb the water. So rather than becoming water absorbent, it becomes water repellent. So similarly, space in this scenario bounces out because it's got filled up. Simple as that. So basically what you do is you find that the Big Bang is, in effect, the Big Bang singularity is replaced by a big bounce. So there was a contracting universe on the other side. Now, it's true in the cyclic model of Steinhardt and ES, they have to assume 2 additional fields. But of course, assuming additional fields is not like some bizarre, weird thing. This happens all the time in physics. The Higgs field is Stephen going to say the Higgs field was some conflict with Occam razor. When you have a problem, you come up with novel solutions. This is what science does. This is completely normal in science. And if you thought this was a great problem, you'd be stopping science in a sense, because scientists are often coming up with novel solutions to stuff. So this is
It's not about circumventing anything.
And the funny thing is that solving a lot of problems with quantum mechanics and trying to merge other fields with quantum mechanics oftentimes comes with, or explaining problems utilizing quantum methods usually comes down to like positing the existence of some field that breaks some symmetry or something like that. That's just kind of how that's approached. And that's because it's been an extraordinarily successful approach thus far.
It's about just testing different ideas, creative ideas.
It's trying to come up with better than what we've got and then seeing what it does.
Yeah.
Now, if you find that it solves certain problems and there are certain reasons to take it seriously. So, for example, if we stay in the loop quantum gravity case, I'm not saying that quantum gravity is right. Okay, it's got problems. Like every theory has problems, including ones with a beginning and ones without a beginning. Every theory has problems. That's why we're writing a book about how people are battling about them. All theories have problems. What does that really tell us? It just tells us that our theories are incomplete, right? That we don't know what's happening. And this is kind of the whole point of the argument here. We don't know what's going on in the early universe. So we can't make any firm conclusions, right? But there's no reason to think that these ideas require a God, right? It doesn't point to anything other than a lack of our understanding. And we try and push forward. It might be that nature doesn't allow us to go
and presumably for you, just before we come back to you, Steve, you believe that, I think we'll need to get to this, towards the end of our conversation. You presumably believe that God is a very unsatisfactory explanation compared to continuing to explore physical, mathematical, other types of
I don't believe any of the models in our book. Okay. Right? And the reason is because I won't believe it until it's made really precise predictions that have been tested thoroughly against observations. So what people in this field are trying to do that. Now, at the moment, it's simplified models. There's nothing, I think, absolutely compelling. I mean, if you survey cosmologists, and in fact, we have surveyed cosmologists, certainly about inflation versus alternatives, because that's one debate. And then even if you think inflation happened, you can ask what happened before, right? So inflation is the most popular model, right? Arguably, it is actually a pre-Big Bang model. In fact, Guth talks about it that way.
Yep.
But we don't know. I don't think there's anything convincing, right? So we basically should be agnostic, right? And if we're lucky, we will be able to push beyond. But it's possible that nature's just put up a brick wall and we'll never know, right? In fact, there's a theorem called Melvin-Manchak theorem, which says we can't ever know the global structure of space.
That's because it was said quickly. Melvin-Manchak theorem is what he's referring to.
I mean, if that's right, maybe we're never going to know. But I mean, I'm a bit more optimistic.
Also, there are some cosmologists that have suggested that if something like inflation did happen, it may be the case that inflation itself destroys information about what was going on in the universe prior to the inflating phase. It may be the case that we will reach a point where there will be no way for us to ever learn more. We will simply never be able to gather the information. That's possible.
More optimistic than that, but it does say, I think, that you couldn't observationally tell the global structure of space-time. But here's the important point. Actually, let me address this issue about putting the information in.
Okay, let's do that, and then we will pass it back to Steve.
So it's true that equations often have infinite number of solutions. So if you just think of a really simple equation like x plus y equals 2, there's an infinite number of solutions to that equation, right? It could be 1 plus 1 equals 2.
1.5 plus 0.5. Yeah.
Exactly. There's an infinite number of solutions. It could be 3 plus minus 1, right? So now when you go to the real world, what you find is that often these things get constrained by the regularities that exist in nature. So imagine what we're actually trying to describe is apples falling off a tree, okay? So let's suppose we have some detector and it can detect a sound of something falling, but it can't tell how many apples. But we know there were 2 incidents. So now our equation is x plus y equals 2, right? Oh, actually, it has to be 1 plus 1 because there can't be a negative number of apples. And there can't be, actually, from what we know about apples, when they fall off trees, they're whole apples. So actually, the infinite number of solutions collapses down to like one unique solution, okay? Now, in field theories, it's true that there are an infinite number of solutions to those equations, right? So how do you make progress? Well, you impose symmetry. One way you can do it is impose symmetries, right? And then you see what you get. Now, a lot of the symmetries might be justifiable by empiricism. So we look at the universe and we see it's homogeneous. So, okay, let's impose that as a symmetry. So what physicists are doing is trying to make progress. It's true that they have to make assumptions. The God theory has to make assumptions. You have to make assumptions about what God would do, whether he's good, what kind of universe he would create.
And this also plays back to Stephen Meyer's point about parsimony here, is that the thing with a naturalist worldview, the thing that the naturalist and the theist can both agree upon, is that there is a natural world. Now, for the naturalist, that's all he's saying, is that there is a natural world. The theist is saying there is a natural world plus at least one other thing, and that's God. So going back to this parsimony issue, that's one more assumption than the naturalist needs to make, which means that naturalism is intrinsically simpler than theism is as a broader metaphysical thesis.
No one can get out of making assumptions, right? But what you do is you have this feedback in cosmology. We don't believe, even if you make assumptions and you get a plausible idea, right? So I think inflation is plausible, right? But we don't believe it until it's got through the incredible number of robust tests. And I think I don't want to endorse any theory, be it God or a big bounce or holographic cosmology, which actually I don't think holographic cosmology does need a Wheeler-DeWitt equation. You don't use the Wheeler-DeWitt equation. You use
No, I'm saying it's used in quantum cosmology,
right?
And
so
certain
the bottom
areas
line
of
is,
quantum cosmology.
Yes, people make assumptions. This is what you have to do physics, and it's nothing unusual. Coming up with new fields is nothing unusual. It's been done before. That's what the Higgs field was. This is part of doing science.
Okay. All right. So
a couple of points.
Let's have some further thoughts, and I'm going to start to bring this into land so we can also talk about our other big issue, which is the fine-tuning of the universe for life and whether that lends evidence for the God hypothesis.
Right. A minute ago, Phil said that we have a lot of confusion about what was going on in the early universe. The word early implies that the universe was near the beginning of its beginning.
Well, no, it just means that it's earlier than in the course of events in the time evolution of the universe as compared to where we're at. That's all that means.
And the multiplication of these very abstract models that do circumvent the beginning, I think, is evidence not of progress in physics. I think models that do multiplication of these very abstract models, the multiplication of these very abstract models that do circumvent the beginning, I think, is evidence not of progress in physics, but of a kind of degenerate research program. That Thomas Kuhn, the historian of science, said that when you see a multiplication of modeling, you're not seeing a healthy research program that's making progress. If there are 25 different models, they're mainly inconsistent with each other. If they require many ad hoc assumptions, a multiplication of explanatory entities, this is not evidence of making progress. What he inadvertently said in referring to the universe as having an early.
So first off, that was not Thomas Kuhn that says this. That was Imre Lakatos, who's the one that proposed the notion of scientific research programs and progressive and degenerative problem shifts in scientific research programs. The fact that there are a lot of models developing is not in and of itself a sign of a degenerating problem shift. Adding more ad hoc auxiliary hypotheses is not in and of itself a sign of a degenerating problem shift. Oftentimes, actually, when you get new research programs developing, there tends to be immediately sort of an addition of more ad hoc hypotheses that then get slimmed down as we collect more evidence. So you can't immediately say that doing this is a degenerating problem shift in the research program. And just to verify that I actually know what I'm talking about, give me 1 second here. I am actually currently reading Imre Lakatos's book, The Methodology of Scientific Research Programs. You can see, well, maybe you can see, I've got my bookmark there. I'm just a little over halfway through it. And yeah, this was, I mean, Imre Lakatos talks about like Thomas Kuhn and some of the stuff that he developed, and he thinks that Thomas Kuhn got some stuff right, but not a lot of stuff right. But yeah, this idea of scientific research programs and the progressive and degenerating problem shifts within them, and adding on ad hoc auxiliary hypotheses to hardcores, and having, you know, a negative heuristic and a positive heuristic and all of these things. This was developed by Imre Lakatos. So yeah, cosmology, I would not say that cosmology appears to be degenerating right now. I do think that we are adding certain ad hoc hypotheses, but doing so is not intrinsically bad.
Early state is the most natural thing that most people think, even in physics, when they're thinking about how the universe began. There was a Big Bang. And so what's taking place is these models are attempting to eliminate the idea that there was a single beginning. There are two basic types. Either you get the quantum approach, the quantum cosmological approach, that wants to portray the early universe as a quantum state in superposition of these mathematical possibilities, or you have either some type of oscillating or cyclic where you have multiple Big Bangs. And Phil interviewed Sir Roger recently. He has this cyclic conformal model. He posits fields that have, again, properties that no other fields have. He has to have exquisite fine-tuning after the crossover from the expansion phase of the universe to a new phase where you have massive entropy, and it's by a kind of mathematical sleight of hand. He reduces that with what he calls scale invariance, and then somehow that massive universe that had lots and lots of entropy is now a universe in a low entropy state with lots of energy available to do work, simply because he's measuring it differently. And then once the universe begins to expand, it has to be the right amount of mass of the right kind has to be introduced by a new type of field. He used to call it a phantom field. Now it's a field of unnamed, that's producing particles called eribons that again have features that no other massive particles have in physics. So what you're seeing, I think, is not a healthy research program, but a proliferation of highly speculative models that are getting around that very obvious conclusion that if there was an early universe, early with respect to what? Early with respect to its beginning. And it would, I think, be much better to simply
early with respect to where we're at.
Acknowledge that there was a beginning and proceed in physics research based on that assumption, rather than the multiplication of modeling that is.
What about Phil's contention here that, you know, this has always been the way of science? People try different things. They get creative. They put out different hypotheses. Inevitably, some of these are going to be difficult to test because of the nature of the.
But absolutely, there's nothing wrong with modeling. The point is, what does the modeling show you when you look at it carefully? It's showing that you have to violate Occam's razor with multiple explanatory entities, and invariably, to make the models work, you have to have exquisite fine-tuning. You can't get a universe like ours with specificity of features without constraining possibility space mathematically. And so
but again, that's something humans do for their physical theories. Personally, I have no problem admitting that our physical theories are finely tuned. It's just then obvious who finely tuned them. We did.
Fine-tuning, it becomes an inevitable consequence,
and we do so because they're incomplete theories
of these models that eliminate a beginning. And so that provides, I think, a basis for a different form of the cosmological argument, an argument from contingency, but still a very powerful pointer to God. You either have a God argument if you start with the assumption of a beginning, with the evidence for a beginning, or if you circumvent that, go in a different direction, model a non-beginning universe, you have to compensate for that with exquisite fine tuning. And I would assert, and I think I can show, that you find that fine tuning in each of these models, and it's not something that's explained within the structure of the model, within the structure of the mathematics of the model. It's imposed extrinsically by the modeler, and that's the input of information I'm talking about. That is, I think, being inadvertently. I think that input of information from the modeler is inadvertently revealing what's necessary to make a universe, which is an input of information or fine tuning.
That's what's necessary to make an accurate model of the universe.
Quick response, and then I'm going to get you to do the trying to understand each other thing. Okay, so quick response.
Okay, so notice that Stephen didn't reply to my point about, let's say, the loop quantum cosmology model. Okay, what was going on there? Nothing metaphysical about it. It's just a collapsing universe and an expanding universe. There's no need for the extra fields that you have in the aperiodic model, right? Also notice that there's no reply to the issue of what does the BGB theorem really prove, right? Oh, one thing I should point out, that it's also based off of particle picture of reality, but we don't think that when we get back to the early universe, we have a particle picture. It's a field picture. Now, when I say early universe, I'm just talking about the hot dense state, okay? Because this is the language that we use. Okay, it doesn't mean, as we said, we can actually show you what physicists think. Okay, and they don't think that the Big Bang was necessarily a beginning. So but yet they talk about early universe. It's just a turn of phrase, right? The idea of making something big about that. Now he says, well, there's all these like exotic ideas out there. Now, of course, the cost of the ideas depends on what they have in each case. So, for example, we challenge the idea that you could have a variable speed of light. You might say that's like an incredibly bizarre assumption. Okay, why would you think that? Well, there are reasons to think that. There's a theory called Hodge-Lifshitz gravity. It's a proposal for quantum gravity, and there's a reason to take it seriously. I'm not saying it's right, but there's a reason to take it seriously.
But
this
that's
is
a
what,
kind of dodge. I'm sorry, Phil. That's a kind of dodge to say I don't take any of the models to be correct, but the very fact of these possibly incorrect models shows that the universe didn't have a beginning.
No, I'm not saying.
But that's not what Phil is saying. Phil, what Phil is saying is that we don't have enough evidence to say any one of the models is correct, but the fact that we're developing models is something that needs to be taken seriously nevertheless. That these models, even if they're incorrect, are serious attempts at trying to carry physics forward and solve some of the problems that we have.
Saying that, Stephen, that's a complete mischaracterization of what I'm saying. What I'm saying is that we don't know what the correct description of quantum gravity is, okay? Therefore, we cannot make any firm conclusions about whether there was a beginning. Therefore, the singularity theorems, which rely on Einstein's theory of gravity or a classical space-time picture, and the Borda-Guth-Vilenkin theorem does require, all right, a classical space-time picture.
Mm-hmm.
And it also requires that the speed of light can't be violated. Well, if Hodge-Lifshitz gravity is true, then the speed of light...
It does not require a quantum gravitational theory.
It's a classical picture of space-time. It absolutely is.
It's based on special relativity, not based on general relativity.
No, but it still
so
requires
the fact that general relativity doesn't apply. It still
requires a classical space-time. It still has a particle picture of reality, right? This is something well agreed upon. Okay. Now, the point is, yes, you posit new things. This happens all the time in physics. Okay. And then what you do is you have this feedback with experiment. So what experimental evidence does the God theory make? Does it predict? So here's a claim made by inflationary cosmologists, and in fact, I think that Stephen very much mischaracterizing this. But so there are simple models of inflation, and they claim to make predictions for, let's say, the degree of scale invariance or gravitational waves and things like this. And in our book, we talk about some of these possible tests. And at the end of the book, I don't want to reveal the ending, but we think there's a much more definitive test that happens. Okay, and the point is, we don't believe these theories until these definitive tests have been done. So what does God say about the level of scale invariance, or the strength of gravitational waves, or whether they're tilted blue or red? As far as I can see, nothing. Right? It's very easy to say, I assume a being that could do anything, and then it can explain anything, right?
Exactly. The thing is that if any one of the 25 models outlined in Battle of the Big Bang were correct, you could still say that God exists. Like, God doesn't make any unique predictions about the structure of the world such that we can go out and measure the world and see if it aligns with that and definitively rule out that God exists by doing so. And most theists will tell you this. You can't empirically rule out God's existence, and you can't really empirically rule in his existence either. You have to use the empirics plus various philosophical or theological assumptions in order to get there. But I think another point here is just God. I don't think God is a good explanation, largely because it's consistent with pretty much any way the world could be. Because the world could be any way, and people could still just be like, yeah, and that's the way that God wanted it. And something that explains everything explains nothing. Because there's no, at least in the sense that most people are going to be talking about when we're thinking of explanations, particularly if we're talking like some sort of scientific explanation, I think, but even in terms of how explanation is used in common parlance, it's usually, I think, going to be some sort of contrastive explanation, sort of a what explains X rather than Y, or something along those lines. And if God can be used to explain any states of affairs, then there is nothing against which you can contrast it as an explanation. And so it's hard then to establish it as an explanation for anything. And it's part of the reason why I think God is not a good explanation for many things, if not most things, if really not anything at all.
Okay, of course you can. But I say that we don't believe any theory until they've been tested. Now, that doesn't mean that something can't have some degree of plausibility. And I think that some of these ideas like string theory, like loop quantum gravity, like causal set theory, they have reasons to take them seriously. So, for example, there are infinities in our equations that can be solved, right? Which you can't do in general relativity. The equations blow up. And in these approaches, equations don't blow up. So that is a reason to take them seriously. It's not a reason to say that they're true, but it means that I think, therefore, when you get this, that is a sign of progress.
Okay.
Because, oh my God, there were equations that couldn't be solved. Now they can be solved. There's a singularity that couldn't be resolved. Oh, we actually show that we can resolve a singularity. I think that's progress. It's far from the end of the journey, right? We need those empirical tests. And until then, we don't say what's right. And I think what's happening with the theist is they don't have anything like a mathematical description of what God would do. They don't have any predictions, but yet they're assenting to that theory.
Well, I'd like to hear Steve respond to that, because I think this takes us into the important question of
let's
the
be clear about
power of
what's
God.
going on theoretically. You go back to, as far as we can go empirically, to the beginning of the expansion, and what all of the models that are described in the book are doing is modeling what came before that. And so there is every bit as much of a boundary empirically to the naturalist or materialist cosmologist as to what precedes the Big Bang as there is to the theist who posits a creator. All of these models are full of unobservables, unobservable fields, unobservable physics, unobservable.
Some of that's going to depend on precisely how one defines unobservable, but there is an extent to which that is true.
Processes that are exquisitely finely tuned. What theism expects, there's a wonderful quote from Dawkins, who I guess you interviewed yesterday. He said that,
I hate this fucking quote.
The universe we observe has precisely the properties we should expect. If at bottom there's no purpose, no design, nothing but blind, pitiless indifference. What's implied in that is that metaphysical systems, materialism, theism, are every bit as testable by comparing what you would expect to see given the hypothesis as our scientific hypotheses. I think what we have in these formulations of pre-Big Bang cosmologies is a form of mathematized materialistic metaphysics, and that the proliferation of these models doesn't show that a promising research program, but the opposite. And that there are things that you would expect to see in the universe that we see in physics that invariably cannot be explained within these models. And one of those key things is fine-tuning. This is something that agents do that natural processes don't do. If you have a vast ensemble of possibilities, and only one or very few of those possibilities is necessary to achieve a propitious outcome, whether we're talking about a French recipe or an internal combustion engine or you name it, these are things that we know minds produce. And in all of the naturalistic cosmologies, we have a transcendent dimension.
The thing with this, well, we see minds produce this all the time argument that I hear is that all the times that we see minds produce these things, they do it through physical processes and in ways that are consistent with natural laws. So, and all the minds that we've ever been able to observe or understand come alongside a brain. So, what's your point?
Something separate from this universe. Theists agree you need a transcendent dimension, but what's missing in all the pre-Big Bang naturalistic cosmologies is an entity which can fine-tune a system. That fine-tuning is always modeled by the physicists.
This is assuming that the fine-tuning is itself a feature of the world and not just merely a feature of our physical theories about the world.
As they gerrymandered the equations. And so that's an expectation, a prediction of theism that is present in the physics.
But what provides for that prediction? Why would God fine-tune a universe? And how exactly would you determine that the universe was fine-tuned? You can't just say, well, I presume that life is special and life exists in the universe, and if we alter its constants by a very small amount, life wouldn't exist, so it must be fine-tuned for that. Well, but that assumes that God would have wanted to do it that way and that we are the end goal. How did you reach that conclusion? So I don't, again, it's going to be very, very difficult to establish that God is actually like accounts for any of this stuff.
Physics that's not expected on.
And this is to answer Phil's objection
Yes.
that God is not an adequate sort of testable.
He wants to say it has no
hypothesis.
empirical content, and I'm saying no, it does.
Well, I would agree with him. I don't think God, as like a metaphysical concept, has any empirical content.
And the very thing that these models invariably cannot explain is the very thing that theism expects, which is present in all of the models.
Right. We're going to take a
My question there would just be, how does theism generate this expectation value?
pause just for a moment, because this is fantastic. I'm racing to keep up with all of this, but I think I'm there. I'm going to ask you both to just at this point where, because I think this is a natural point to maybe start to transition into our other big topic, the fine-tuning of the universe, and we'll do.
Okay, so that's the end of the cosmology kalam part of Phil and Stephen's discussion. The next one is going to be fine-tuning and teleology and all of that stuff. So just to wrap it up here, I really think that Phil did a phenomenal job in this discussion with Stephen. I think, at least thus far. I mean, obviously I've watched the whole thing, but I really like how he does push. He meaningfully and respectfully pushes back against what Stephen says, and he does a really good job of emphasizing where it is that the physicists actually stand and what it is that the data that we currently have and the models that we currently have are actually capable of doing, and what kind of conclusions we are actually capable of meaningfully drawing from them. There's and the topics discussed are ones that there's a lot of atheists out there that just really aren't up to speed on a lot of those kinds of arguments and all of the surrounding discussions, like Phil is, which is one of the reasons why I really like what Phil does. But I just was very quite impressed with the sort of the it seems like a strong word, like that Phil was a little bit more aggressive. Like he wasn't afraid to push back and be like, yeah, that's not correct. That's not how this is looked at. Because I think that we need more of that that's the approach that you need to take when you speak with somebody like Stephen Meyer. Not that I think Stephen Meyer is dishonest, because I don't. Like I said at the beginning and then in the middle of the stream, I think Stephen Meyer is a lot more formidable than people give him credit for. And I think that he's a cut above a lot of the other apologists out there, even within the Discovery Institute, which Stephen Meyer is a part of. But I think Phil did very, very good explicating the BGV theorem, the Borda-Guth-Vilenkin theorem, explicating the importance of needing a model for quantum cosmology, and just really summarizing where the field of cosmology stands today with respect to these questions. And with that, I'm going to leave it there. Stay tuned for part 2. Probably won't happen this weekend. I'm going to do it sometime next week. Tuesday or Wednesday would probably be the days to look out for, but I am going to do a part 2 and go over their discussion on fine-tuning, because there was a lot of there. As those of you who have been with me for most of this stream or have been in and out, there was a lot packed into this discussion already, which is something that I really liked about this discussion, is that they covered a lot of the points I think need to be covered in this discussion. They did well defending the positions that they're taking. The challenges they provided to each other were meaningful. These are the kinds of discussions that I definitely like to review for those reasons. But I am going to end it here. I hope all of you enjoy the rest of your Friday night as well as the rest of your weekend, and I will see you in part 2.